Welcome to Lesson 8 on redox processes. Today we're going to talk about electrolysis, specifically molten salts and water, and how we can select which ion migrates to which electrode in electrolysis. This process is called selective discharge. From last time, we looked at the difference between voltaic and electrolytic cells. We know by now that voltaic happens spontaneously. That's why they're able to convert chemical to electrical energy. Electrolytic is a little bit more difficult. That's why it's non-spontaneous and requires a DC power source to convert electrical energy into chemical energy. We also saw the example with a rechargeable battery and how it works as both a voltaic and an electrolytic cell. We also see the difference of voltaic cells having two separate beakers immersed in the ions of whichever metal electrodes they are in. However, electrolytic cells, they use the same inert electrodes or graphite, and they are immersed in an aqueous electrolyte containing the molten salts. Today we're going to look at 9.2 and 19.1 of the IB standards again. Electrolysis of molten salts. Because electrolysis requires molten salts like we saw last time, that means that they don't have a solvent, right? There's no solvent. The solvent is the molten salt, is the electrolyte. So there are only the ions from its compounds. So because they're molten salts, the ions from its compounds, for example, sodium chloride becomes sodium cations and chloride anions. Therefore, one of each of the ions migrate to each electrode. But let's have you guys try this question first, and we'll move on to talking about selective discharge. So you guys should remember that the anode is oxidation always, cathode reduction always. Anode attracts anions, therefore the electrode is a positive electrode in electrolysis. Cathode attracts cations, therefore in order to attract positive you have to have a negative electrode, right? So that should have been your process in determining this question. Let's take a look at sodium chloride as an electrolyte example in electrolysis. Because making sodium chloride to form its ions is rather difficult, usually requires very high melting point of 800 Celsius. So you usually mix sodium chloride with calcium chloride in the electrolyte. That way you can decrease the melting point a little bit in the industrial process from 800 down to 500. But another question that might arise is, well, then doesn't that mean that calcium would also try to, migrate towards the negative electrode in the cathode? Well, no, in fact it doesn't. So take a look to the right. Added calcium chloride to reduce melting point. Do you see how the calcium compared to the sodium, the electrode potential is negative 2.87, and the standard potential for sodium is negative 2.71. So because cathode is reduction, and we know that reduction happens further down the reactivity series, right? Whatever gets oxidized down to whatever gets reduced. So because sodium is below calcium, so we know for a fact that sodium is the one that would migrate and will be preferentially discharged. Chlorine, on the other hand, does not have anything to compete with, obviously, because calcium chloride is simply chlorine. So chlorine, then the chloride ions migrate to the anode. Electrolysis of aqueous solutions. So now let's look at aqueous. Aqueous solution is different from just molten salts, right? Aqueous solutions, remember, when it's aqueous, there is presence of water. So it'll be harder for us to determine this because now we have water that's competing with the oxidation or reduction half reactions. So they're also interfering with the molten salts. For example, water can be at the anode. Water could also be at the cathode. So what can we do? In this case, if you look at the anode and the cathode, these two equations are different. So these two half equations, one anode is oxidation, so that reaction shows oxidation of oxygen. Cathode, this one shows cathode is reduction, right? So this one shows the reduction of hydrogen. That's why they're two different half reaction equations. These half equations, you can find these on table 24 of the IB Data Booklet. But also, we have to remind ourselves that there are anions and cations present. So water is going to interfere with anions and cations. So when we choose which one goes towards the anode and which one goes towards the cathode, we have to look at the electrode potentials of water and the anions and the cations. This is called selective discharge. Today we're only going to look at the relative electrode potential, standard potential values of the ions. There are two other ways that selective discharge occurs, and that's in relative concentration and also in the nature of the electrode. So today we're only looking at the first one. The first one is the electrode potential values. Electrolysis of water in an ionic compound. So let's start with an example. Water, we know from chapter 8, they're not a good conductor of electricity. So this means that ionization is pretty low. When we add ions like ionic compounds of sodium hydroxide, we know that from electrolysis, this is the opposite, right? The cations go to the cathode and the anions go to the anode. So being anions of hydroxide, that one would go to the anode. Cation, being sodium, would go to the cathode. But now we have at the cathode, remember we talked about water can also be at the cathode because of it being an aqueous solution. So we have to select which one, the sodium or the water, is preferentially discharged. And at the anode, we have another. We have the hydroxide and we have the water. So which one do we choose? Remember, let's take a look at the reactivity series again. Reactivity series is on table 25 of our data booklet, and it corresponds exactly to the electrode potential values in table 24. So it's in the exact order. We know from the top, they're really good reducing agents, right? Which means they're really easily oxidized. At the bottom of table 24 and 25, they are oxidizing agents, so they are very easily reduced. So when we look at cathode, cathode is reduction. Because cathode is reduction, we look at which one is further down near the bottom of the electrode potential list. And we know that it's this one. So let's take a look at the anode. The anode is oxidation, right? So oxidation meaning it should be more easily oxidized, so it should be near the top of the list. So when we compare these two values, remember these are the reactivity list, the electrode potential list. Usually they only show half equations in reduction way. So when it's oxidation, remember you have to flip it. That's why when you flip these half equations, you add a negative in front of the electrode potential values. That's why these two have negative theta E's as opposed to the cathodes where there's no negative in front of the standard electrode potentials. So taking a look at these two, before we add that negative, we see that the hydroxide is further up the reactivity series than the water, right? We see that the 0.4 is further up than the 1.23. So we know, in this case, that the hydroxide is preferentially oxidized. So after we figure this out, then we multiply both of them by a -1, and that's why the hydroxide has a negative 0.4 volts as opposed to just 0.4 volts. Remember again, you have to add the -1, you have to multiply the electrode potential by -1 when you're doing oxidation, because all the standard electrode potential values are in the direction of reduction. So if it's oxidation, it has to be swapped. So you multiply by -1. So the overall reaction, we then know that at the cathode, it's water. So water is preferentially reduced. So because it's preferentially reduced, we see that hydrogen is discharged. At the anode, the OH, hydroxide, is preferentially oxidized. This means that the oxygen is discharged. And we see this from these two equations. From these two equations, we then again calculate overall balanced equation by multiplying by however many moles total to cancel out the electrons. So we multiplied the first cathode equation by 2 so that all the electrons are 4 electrons in anode and cathode. That way we can cancel the electrons out. We find that the overall balanced equation for the electrolysis here is water. So water becomes hydrogen and oxygen. Therefore, from this we can see that the selective discharge of ions depend on the relative standard electrode values, the ion concentration, and the nature of the electrode. Here with this example, we just saw that the selective discharge of the ions depend on the relative standard electrode values. Now let's take a look at the electrolysis of water and the reaction prediction. So from the previous equation, we saw that it was 2H2O yields H2 plus O2. So we know that the production has colorless gas of H2 and O2 at both the anode and cathodes. The ratio of the gases are 2H2 to 1O2, and we saw that from our overall balanced equation down here, 2 moles of hydrogen versus 1 mole of oxygen. We also can see, let's take a look at the cathode and at the anode. Do you see how at the cathode, because H2 is preferentially reduced and H2 is discharged, we see a hydroxide being released. So because the hydroxide is released, that means that at the cathode, there would be an increase in pH, right? Hydroxide is more, basic. So there's an increase in pH. At the anode, let's take a look. I went back to a slide before. At the anode, do you see how there is a release of hydrogen ions, although it's not the one that's preferentially oxidized, although the water equation isn't, but it's still present, right? It's still present in the solution in the electrolyte. And so at the anode, we see a decrease in pH. So give you a moment to write down what does the pH of anode and cathode become. Does it increase or does it decrease? You don't have to give a number, just say whether the pH increases or the pH decreases. So you might be like, why does this even matter? Well, the electrolysis of water actually produces hydrogen gas that we use all the time. Hydrogen gas by itself is used in creating acrylic paint, is used in whether it be making glassware or freezing fruits. It can also be used as hydrogen gas to fuel hydrogen-fueled cars.